Good evening, everybody, and welcome to, I think, what we might call the grand finale of World Geothermal Day. We thought we would use the occasion of the World Geothermal Day to spread the word a little bit more about our York's adventure into geothermal. I know there's been quite a few events in the city during the week. I hope you've had a chance to visit some of those, see some of the actual hardware. I can see some nods about the seismic survey and the huge map that we've got just across there. We've perhaps walked across the geology of the United Kingdom. I hope you've been able to absorb some of that. If you haven't, we've got a treat for you in store this evening. So I'm Sarah Thompson. I'm the Pro Vice Chancellor for Research here at the University of York, and I find it really quite inspiring to live in both a city and work at a university that is really committed to net zero ambitions. But it's one thing to have ambition, it's quite another to be able to put them into reality. So I'm really proud, actually, that at the university, and largely due to the man you're going to hear from this evening, that we've been able to take the initiative and to explore the possibility of geothermal energy to really realise some of those ambitions and to be at the forefront of the implementation of such a transformative technology. To be able to do that requires substantial funds, and hence we are really grateful to the UK government to fund that project to the tune of something like £35 million from the Department of Energy Security and Net Zero. And I should also say that as well as our two speakers, which I'm going to introduce to you in a moment, we have our local MP, Rachel Maskell, with us this evening, and she's going to wrap up the evening with a few words about her perspectives and interest in this project. So we're delighted that you're here this evening. We've got two speakers. They're both going to speak for about 20 minutes, and what you're going to hear to start with from an expert is about the science and about the context and the global history, if you like, of geothermal energy, which will set the York project, set the context for that. And then we're going to hear about the project here and what it is going to be in reality. So, our speakers then, we're first of all going to hear from Professor John Gluyas from the Durham Energy Institute and the UK National Geothermal Centre. So, John's had quite a career. He's moved from fossil fuel exploration to research on decarbonisation, geothermal energy, hydrogen and helium potential, and all with a real focus on the consequences of energy production on society and industry. After working for some years in the oil, gas and energy sector, John's led groundbreaking research in geothermal energy and the exploration of alternative gases. Alongside that work on helium, John's been one of the leading champions of the potential of geothermal energy and was instrumental in establishing the UK National Geothermal Centre in 2024. Not only are we delighted to have him here this evening, but he's been a huge supporter of the project here in York, so he's really part of the team. Then we're going to hear from Paul Bushnell from one of my colleagues here at the University of York. Paul is a chartered engineer. He's got over 35 years of experience. He's led and managed numerous engineering and infrastructure projects over this time. He's the major driving force in the university's decarbonisation strategy overall, and is really interested in how we deliver sustainable low-carbon infrastructure. He's been the instigator and motivator of our deep geothermal scheme right from the beginning, and now he's got the somewhat significant task of being its overlord, I think is probably the best description, and responsible for spending that £35 million wisely. That's our money after all, and we need to spend it in the very best possible way. Just before I hand over, I realised I've forgotten to do the housekeeping, so my colleagues are going to be, will be cross with me. In the unlikely event of there being an emergency, please follow the instructions, and there are fire exits over there and over there. Right, I'm going to hand you over now. First to John, we'll go straight on to Paul, then we've got time for questions, and there'll be roving mics, So keep all your questions for that opportunity at the end.
Professor Thompson, ladies and gentlemen, it's a privilege to come here on World Geothermal Day to tell you a little bit about how geothermal works. And I am just the warm-up act for Paul. So without further ado, you've heard a little about me, and what I intend to do is take you through what I hope is the big picture, and then we'll drill down, that was accidental, drill down to the situation in York. Carl Sagan described the Earth in 1994, following on from the Voyager missions, as a pale blue dot hanging in space. For sure, it is cool, and yet it isn't. And if we look inside the Earth, there is substantial amount of heat, enormous amount of heat. The temperature in the core is something like 6,000 degrees centigrade. And although it won't shine white like that, because it's buried beneath all those layers of iron and then rock, it's very, very hot indeed. It's hot for two reasons. It's hot because of the condensation of all that matter 4.5 billion years ago, and it's hot because it contains three elements which decay as radionuclides: potassium, uranium and thorium. No one's quite sure of the balance between how much heat comes from those primordial setting and how much heat is added by the decay, but don't worry, it's been hot for 4.5 billion years. It will still be hot in 5 billion years when the sun ceases to consume hydrogen, flips over to helium and expands and consumes the Earth. So we're okay. Some places are hotter than others, quite clearly. Now, there's a couple of videos here. We'll just listen. No.
Oh, I missed it. My camera's not working. I didn't take the picture.
It's always like that.
Oh, well, now it takes pictures now.
Oh, we'll get another one straight ahead.
Oh.
When, all right, girls. When I first heard that, and Paul was the same, oh, those voices, they mess up the story, as it were, it interrupts. But no, that's the joy of geothermal, quite literally. And it's not often we hear the science, if you will, gets right to the heart of people's emotions. That's unusual. Yes, Iceland's super hot, places in New Zealand are, and so on. So let's ask a few questions of geothermal. It might have revolutionised, in fact, over the years in Iceland, completely revolutionised the atmosphere. In 1948, Reykjavik had smogs like London did in the 1950s. And it was the use of geothermal which has helped change that dramatically. If we think about availability, sustainability, security of energy supply, a big problem of late, emissions, of course, and Sarah touched on those, and building and operating costs. Let's just play around with some of those. It's available 24/7 or 365, however you want to describe it. The base load is there. It's always there. Sustainable, well, we've done that. It's here until the ends of the earth. Yes, everywhere beneath your feet. It doesn't matter where you are on the planet. If you drill down beneath your feet, it gets hotter. Anybody been down a deep mine? And it's warm. Yeah. In terms of emissions, there are some tiny quantities of emissions occur with some volcanic systems of CO2, as they would do naturally. But as far as the UK, or indeed many places around the planet would be, there aren't any emissions. There are no gases, nothing to clutter up the atmosphere, no particulate matter. Yes, the build costs, certainly, you've heard something of that in the introduction from Sarah. The build costs can be high, the operating costs are exceedingly low, and the systems last for decades. A couple of examples. We've used geothermal heat in places like Bath, since pre-Roman times. No volcano in Somerset, but plenty of hot water coming out of the ground. Laredo in Italy, I've lost the date off that, 1904, was the first power ever generated from, when I say power, I mean electricity, from geothermal energy. The biggest system in the world is the geysers in California. It's been operating since 1960. And coming closer to home, Eden, that's Cornwall, I know it should be Yorkshire, but that's Cornwall, and the Eden project is now heating the greenhouses on site with geothermal energy from a well drilled 5 kilometres into the granite down in Cornwall during lockdown. The neat thing about heat, let's switch to power. If you switch on the light, it comes on, but you've used up those electrons, they're done. You can't then take that and do something else with it. But heat's a bit different. You can take heat, high temperatures, it's a very small volcano, that one, on the top right-hand corner, and you can generate power should you so desire. You can then take the waste heat from that, and you might use it for drying timber, or you might use it for food processing. Coming down a bit further, you can use it in your house, or in your greenhouse, or even for your fish farm. But let's unpack the food processing bit a little bit more. I don't know where these little quartz circles have appeared from, but what I've done is taken the average thermal gradient in the UK and sort of put the sort of depth you would need to do some of these processes. So, what have we got? Milk pasteurisation. Well, the heat at about 1.5 kilometres, anyway down to about 2.5 kilometres, would be sufficient to do your pasteurisation. If you're only doing anaerobic digestion, the reason anaerobic digestion is not really taken off in the UK or anywhere in large scale is because you require an awful lot of heat to kick off the process. And that takes energy, and that takes power and cost. All right, let's remove that. Let's use the earth to do the work for us. And all of a sudden, the economics begin to look quite a lot brighter. So, where is the place to go for geothermal energy? It's very difficult to get the stats on heat, much easier to get them on power, so electricity. So we'll start with power and we'll go on to heat. The US is the big one. And then followed by areas that you would easily decide, you'd throw, yes, of course, Kenya. Yes, of course, New Zealand. They're very high thermal gradient. There's lots of heat associated with the volcanoes in those countries. But, the US out there at the top. No volcanoes in, most of it's in West Coast California. Well, there is, of course, Mount Washington, but we're a long way from that. One of the other interesting pieces of information I put on here, and this is, the measure on this scale is in megawatts, gigawatts, no megawatts, 1, 2, 3, yeah. Megawatts that's a unit of power measurement. And if we look at the total around the curve, if you like, of those nearly 17,000, actually that's pretty small compared with what we generate for electricity in the UK. And so, although California and other countries are big, in terms of the total power that's used, geothermal accounts for about 1% globally and could do so much more. When it comes to heat, the figures are different in terms of the way they're portrayed as well. And you could convert from terawatt hours, which is megawatts or gigawatts over a whole year, so energy rather than power, and China comes up tops by a long, long way. And Iceland is building fast, but again, there's lots of heat in the ground that we could use. Let's look at geothermal potential, or rather, let's think about the way in which we're approaching decarbonisation in the UK. This was a snapshot of emissions a couple of years ago, early 24 or so. So we liberate to the atmosphere around about 1 million tonnes of carbon dioxide per day. That makes it easy to remember. If we think about these different components of the UK economy, I'm slightly concerned by the lack of wheels on that car, but we're going to take them one by one, at least the major ones. We have a plan for decarbonising our transport system. For cars, it's likely to be a lot of electric cars, already taking off, as it were. For rail, it would be a mixture of power generated from renewable sources and hydrogen. Shipping is not on this slide. There's a huge project in Durham to decarbonise shipping. Although, if you look at the news today, it's hit an orange bump. If we look at electricity, we have been phenomenally successful at decarbonising electricity over the past 20 years. You can see the carbon intensity on that black bar chart drop dramatically, and you will have heard the news last year that we ceased to have any coal-fired power stations running whatsoever. When it comes to heat, the situation is a bit more difficult. We have had some initiatives for decarbonisation of heat, the renewable heat incentive, but they've not lasted long and they've disappeared. So very little at the moment. So as you can see, 3/4 of all heat comes from burning fossil fuels in the UK, either directly in your homes or indirectly in power stations. And so heat is the real elephant in the room. When it comes to geothermal, the areas that are not suitable for geothermal in the UK are shown in this tan colour. And the areas that are suitable are shown in green. I've done some little, what they call cartoons or icons on the middle piece. If you drill to 1 kilometre, you can get water warm enough for your bath. 2 kilometres, traditional wall-mounted radiator. 3 kilometres, the heat is sufficient to boil a cup of tea, or even a kettle full. And if you go deeper, we can generate power. Those are sort of rules of thumb. Have we drilled that deep in the UK? Well, of course we have. We've mined coal down to 4,000 feet, or 1.2 kilometres. Onshore oil and gas wells typically drilled to about 2 kilometres. Offshore in the North Sea, 10,000 wells have been drilled. Every one has found hot water at 3 kilometres all the way to 6 kilometres and so on. So we have the technology to be able to deliver that. And in terms of the geology of the UK, you might like to walk over the map next door. It's complex, but we can sort of divide it into 3 bits, as it were. There are granites, which, as many people know, tend to be quite warm because they contain the uranium and thorium which decays to produce heat. And they're well developed in the southwest and the northeast and parts of Scotland. We have sedimentary basins. We're sitting on a sedimentary basin here, and at depth there will be strata, layers of rock, sandstone, limestone, which will have hot water in them. And then there are other areas which have been mined. There are 23,000 abandoned, flooded mines in the UK, almost all of which are coal mines. On the right-hand side, you see a typical geological map, and all I've done there is put squares on where things are happening. Yes, including the North Sea. A granite development in the southwest, an aquifer development in Southampton, and mine developments in the northeast. And soon, of course, we'll be able to add a blue aquifer over York, a blue square over York. The systems, broadly speaking, you've got to use, well, you don't have to, but water is the best way of getting heat out of the ground. And you can circulate that through the ground or within closed system wells. This is what we're doing up in the northeast as far as is concerned with mine water. We're abstracting heat from flooded mine galleries, using that to heat, and I'll show you a couple of examples in a minute, different buildings, and returning that cold water somewhere else such that it can circulate back through and have a chance to be warmed up again. There's some delightful diagrams that the BGS has put together, many more than this, but these show a couple of other systems. On the right-hand side, you've got a coaxial. So all that's happening there is a finger in the ground. It's rather like some of the ground source heat, but it goes deeper. Water is circulated down the outside of the pipe, the annulus, and comes back up the centre of the pipe, and that will take a small amount of heat out of the ground. If you circulate the water within the ground, within a deep aquifer, or perhaps within fractures in a granite, you'll get more heat out. And there are about half a dozen different configurations. When it comes to developments, we've already got three developments in the northeast taking heat out of mines. Lanchester Wines heat their wine warehouses to about 19 degrees centigrade directly from the mines beneath them. The Gateshead Council have been preeminent in the northeast and have developed their mine water heating scheme, which delivers about 6 megawatts. And in the next, well, you can buy a house now in Seam Garden Village, the area where Billy Elliot was filmed, and the heat that goes into that house is from the mines beneath. They're quite hot, about 20 degrees centigrade. In terms of aquifer, in 1973, the UK, or the global oil crisis, set a little bit of a panic in the UK, and we eventually got round to drilling 7 geothermal wells. By the time they'd completed, we were an oil nation, and the only one to survive was at Southampton, where the city's geologist, no, he wasn't, it was the city's accountant, said, I will have that well. He made a geothermal system from that, which you see in the building on the left-hand side. What I've shown on the right-hand side is the Witch Farm oil field, not that far away. Now, what I want you to look at is the blue curve and the purple flat line. The purple flat line is the heat coming out of the single borehole in Southampton. The blue curve is the wastewater at much the same temperature coming out of the Witch Farm oil field. Had BP and subsequent owners decided to do so, they could have heated every retirement home in Bournemouth forever from the waste heat. And what you see in the bottom strip is Ladram Bay. This is the sandstone which is delivering the heat. It's about 2 kilometres depth and 75 degrees centigrade. And what we've seen in the last 5 years is drilling for power. It's the geothermal plant on the United Downs site. It should come on to generate the UK's first geothermal electricity this year. We're waiting still a little longer than we expected. And I've already shown you the geothermal heating system developed by Tim Smith and the MD, Gus Grand, standing to his right. What you're all dashing off to the loo. So let's take a quick look in the last minute or so at what you're trying to do, what you're hoping to do in York. Basically, you're hoping to engineer a system which replicates the hot bath at Bath. And it comes from the same limestone interval. Everybody here will know Malham Cove. Limestones typically are cavernous and fractured. And what you saw on the right-hand side in the video that played is a picture I took just 10 days ago down Ecton Mine in northern Staffordshire. It's where the Duke of Devonshire made all his money from copper mining. And what I wanted you to do was hear the sound of running water. If you have a lump of that limestone in your hand, it doesn't transmit fluid, but they're fractured, and you see the fluid moving into that mine under gravity. That happens to be rainwater. If those systems exist at depth, and we'll hear quite a bit more from Paul, then that's what we're talking with. So, just to round off, in order to develop geothermal energy in the UK, I've been whittling on about it for a decade or more, and it's been quite difficult to get ministers to, or anyone in a sort of power position to take much notice. And so what we did last year is founded the National Geothermal Centre. This is a COVID baby. Conversations, instead of it as playing quizzes of a Monday night, we discussed the potential for delivering UK as a geothermal nation. We need to look at infrastructure, technology, policy and regulation, and of course research and knowledge. Do that, we believe, we've made these as commitments to facilitate the UK to supply 10 gigawatts or so of heat, 1.5 of power, at least 10 million, I think that's a bit of a low claim, to be honest, 10 million tonnes of CO2 reduction, and this number of jobs. Now, if you think about it, there are 37,000 jobs currently used in the petroleum industry, a dying industry, reskilling, opportunity to bring in-house knowledge. There's 250,000 in the supply chain, so here we can probably mop up at least half of those. There are opportunities for training the graduates that come out of York and other universities to deliver this for the UK. I think we can make the UK a geothermal nation. Thank you.
So, my name's Paul, as Sarah said earlier, and John's given us a very good introduction to how geothermal works. Now what I would like to talk about a little bit about how we're going to make this work in York. So where did it really start? York as a city and the university, we've got, let me just call it a duty to get towards net zero. We have to do better. We have to burn less fossil fuels. And we've looked long and hard about that at the university. What can we do? As John says, electricity is quite easy in many ways. Looking at heat is a much more difficult problem. About 80% of our carbon emissions at the university, our fossil fuel burning, come from heating buildings, come from our heating systems. So we scratched our heads quite a lot, thinking about what we can do and what solution, and it's been difficult. It's been really difficult. Part of one of the things we looked at is we did look at geothermal. We looked at that. We didn't think it'd necessarily be successful, but then we got some reports done and we found something. We found this carboniferous limestone layer underneath York. Well, I think everybody knew about it, but what we found was what potential that would be, just for York, not just for York, but for the UK as a whole. Because as John said, there's a lot of potential that we've not quite harnessed yet in the UK. So this project, there's more of it. There's a few key things we've got. We've got a scheme we know we can deliver. We've got a delivered scheme. We've got funding for it. We've got a university. It's fantastic doing a scheme like this as a university. It'd be a real living lab, a real place for students to learn, a real good place for research. We've got skills for the future. We're the next generation of engineers, geologists. How can we exploit this? How can we convert from the oil and gas industries we've got today into a new, more modern technology? And again, we've got a city. We've got a city with strong ambitions. It's great to have the MP here today. And being able to have new solutions in a city as precious as ours is really, really key. I think I've said most of this, but but where we've got from, we had this idea, will it work here? And we've spent the last 12 months or so really refining that, getting more surveys, getting more information, proving that there is this potential there. So what's the detail of our plans? Well, first of all, really need to thank the Department of Energy, Security and Net Zero and our colleagues at Salix who are in the room here as well, in the fact that we put in a bid, obviously a very good bid, and we've been awarded a £35 million grant as part funding towards the scheme, and the university, seeing the potential of the scheme, is adding £5 million of its own funding. And out of that, we're doing quite a few things. So we've got the geothermal well, which we'll talk about in a minute. We're going to it, anybody who knows the university might be aware that we've got a district heating system. What that is you pump hot water around our buildings and heat them up. This building's heated up in that way. So we're going to extend that to more buildings within the university. We're going to improve our lighting, put more LED lighting in place, improve insulation in a set of buildings. And out of all that, we've committed to decommissioning a whole set of fossil fuel boilers. You know, we can't use them again. We've committed to Salix. They're going to be turned off. They're going to witness them being scrapped. So that puts us in a really good position for heat and also opens up further potential. We've got ambitions to produce electricity from the source. We've got aspirations, maybe we can use it elsewhere, maybe we can use it elsewhere in the city. So what's our timeline? We've got a fast timeline. So the project needs to be completed over a 3-year window. At the moment, roughly what it looks like in 2025, we're really about the planning stages. We've gone through a planning pre-application process already. We'll be putting in a full planning application in the next few weeks. We're doing a set of surveys to make sure everything's safe, to make sure everything will technically work. We're about to commission a 3D seismic survey, which I'll talk about in a short while. And we've got to do all our designs. In 2026, we'll be preparing the site, which again I'll talk about a little later on. We'll be mobilising the drilling rig, which will probably come in internationally. You know, it's such a size of project, it's using very specialist equipment. And in 2027 is when we'll be doing the drilling, testing, final connections into our systems. I won't talk through all of this, but it just gives a bit of an example of some of the surveys we're doing. You know, we've got a very precious area in the university. We've got a large focus on sustainability. We want to do this project, we want to do this right. So everything we need to do, and several things more, we're doing and getting close to completing. These are just a few diagrams of some of the things that will be going along shortly. I can never pronounce this right, but we're doing a hydrogeological risk assessment at the moment, which is looking at where the waters flow, these layers of water that John was talking about, working out how the temperatures will change, where the flows are. There's a survey we're doing shortly with the seismic trucks, which I'll talk about, and we're going through making our concept well designs. And for the design we're doing what's called a doublet, one well to take water out, one well to take water in, and those wells are constructed with a series of casings, those great lines. So it's like a tube in a tube in a tube, and each tube supported by concrete. So where are we going to do it? So if you look at the, where am I going to say? Yeah, in the east side, there's where it says location, there's that red mark. There's a red mark on this plan. That's showing where the site is, which is just south of the York Sports Village. Zooming into the site, for anybody who knows York, there's quite a large cycle track that's very heavily used. Just in front of that cycle track, there's a velodrome. The velodrome's currently not being used for 2 years. There's challenges with outside velodromes. Basically, you can't ride on them when it's wet, and unfortunately, we can't predict when it's wet. So the velodrome's currently unused and in quite a poor state of repair at the moment. So what our plan is, that's just a little picture of it. What our plan is to produce 2 boreholes there, each about that kind of size. And to do that, we need a drilling rig, which that one's from the United Downs project, I believe, which is a piece of equipment about 55 metres high that will be on site for about a year. And there'll be a bit of temporary storage. So how we arrange that is, I'll talk about the disruption first. So what will that do? What will people notice with that? So there'll be some local noise, although the initial assessment said it won't be heard much outside the site area. There'll be some minor localised ground vibrations, but you'd have to be quite close to the site to feel them. There'll be monitoring in place for all of those, and obviously there'll be conditions as part of our planning application. If you saw for the picture earlier, the drill will be lit up. There'll be people working on that. And we've picked a site where it's already floodlit. You know, it's already floodlit for sports pitches and so on. And it's quite a long way away from the wildlife. And we will have an impact of a bit of construction traffic. But we've got that schedule, but we've obviously got the A64 access and up by the park and ride site, so that should cause minimum disruption. And one of the key things that's worthwhile saying in picking that site is we've picked a site that's a long way away from residential areas. So that's the way the site will look. The green area, the bright green area in the middle is where we'd have the drill pad area. We're looking to put in place a temporary lagoon, which is the dark green area just to the right of that, to store water and as we drill the well. We'll put in a bit of a laydown area because we've got 5 kilometres of pipe to store, which I'm assured will fit in that space. And we'll have a few site cabins. Now, the interesting thing on the geothermal jobs is once they're complete, there's not much required on the top surface. So it gives us quite a few opportunities for making something quite wonderful once the site is complete. So because we're losing a cycling circuit, one of the things we want to do is to maintain that and enhance that. So the plan we've got, I don't know whether I can point with this, but on the right-hand side of that plan is what we want to do is create a learn-to-ride circuit. So we've been talking with British Cycling and how best to replace the velodrome, and they're very supportive of the idea of us introducing a circuit where children, cyclists that are maybe not that confident, cycling where disabled youth cycling, for example, where we're providing an area where people can learn to cycle in safety, get used to road conditions or what to do on the road, and prepare them for going on the main cycle track. We're also looking at whether we can use the material that made the velodrome initially to produce a skills area, which we're looking to do at the north side of the site. So a bit of humps and bumps for people to cycle over. One of the things we're thinking about, and we're really interested in people's views, is what to do with the lagoon where we're finished. Whether to make it into a wetlands area, so that'd be really, really good from a wildlife perspective, or whether that's something that we maybe shouldn't do with how we're using the area with children around and so on, and what the compromise may be. So we're really quite interested in to see what people think. So talking to the today and what's coming up in the first part of what we're doing for works, which I know a lot of people will be interested in, is we're carrying out a seismic survey. And that's going to be happening over the next month or so. And what is a seismic survey? Unfortunately, we can't see under the ground. So we need to find a way to identify exactly what the geology is underneath our drilling site area. And to do that, there's a technique that's been around, what, 40 years, maybe a little longer than that. A long, long time.
Used to identify where your enemy's ordnance was.
So there you go.
100 years or more.
Well, hopefully we won't find enemy ordnance, but what we're doing is we're going to do a seismic survey over the next month. And the way that works is we put in some nodes, probably about that kind of size. We're going to put about 5,000 of them in grass vergers, farmers' fields, people's gardens. We've got lots of people volunteering to put some in their gardens. And what they do is that they will listen to any vibration in the earth while they're in place. And then what we do is we drive around with a special truck, maybe overgrown bin lorry kind of size. And that truck's got a pad on it. And that pad goes to the ground, vibrates the ground, and all these sensors listen to whatever's recorded back. And we're recording that over about an area of about 4 kilometres to the north, 4 kilometres to the south, because to look 4 kilometres down, that's the spacing that's required. The map here shows roughly where the survey will be. There's a more detailed one, and indeed, I think sometime this weekend, an interactive one on our website. So it gives a little bit of a flavour of where we'll be doing the sampling. As you can see, a lot of the work will be on the A64, which we're tying into an existing road closure. So we're tying in nicely to minimise the disruption. As I say, I mentioned, I think there's still a few spaces left. We're asking people if they want to have a node in the garden and they live in that survey area. There's a way to sign up on our website, and if it is, then we will be in touch. So that's the timeline, kind of describe that. So where we are for the future, that's our next step. What could we do? It's really a set of questions, really. So we've got the scheme here. We'll go through, we'll work through, we'll deliver that scheme. We've now got questions, what else could we do? What else could we think about? Can we think about use of this type of heat further in the city? Is that a potential for us? A lot of the cities, they've got listed buildings, heritage buildings, spaces where it's difficult to put things outside of properties. Could district heating be a part of that solution? Can we use this to get more new jobs? Can we do this to transfer more skills, do more training? With Sarah leading, we're looking at research. We're looking at what extra research we can do. We're speaking with other local universities, well, quite wide field universities, to see what we can do, to see what we can pull together to use these funds most widely and help lower prices, make it easier to do future schemes. We're thinking quite hard about what we can do with schools, what we can do with education, what we can do with the university as a living lab, and really help use this and let people, give opportunities for people to learn and people to explore. So hopefully that's given a bit of a flavour. We've got one of these QR code things up there, although you can just type in Google York Geothermal, you'll get there, to where you can give us feedback. We're also being really keen to keep our website up to date. So keep on looking. Whenever we've got information, we'll put it on there. Okay, thank you.
So questions? Who would like to? Man at the front here.
Hello. You spoke a lot about Campus East, and I just wondered whether you had ambitions to be able to heat and power the rest of the university.
Absolutely. So, as I said earlier, we've got a district heating system in the university. The heating system between Campus East and Campus West is actually already interconnected. So we've got two energy centres, but we can push flow between them. We've already done tests. We've actually ran Campus West off Campus East. We didn't make a lot of song and dance about it, but we've tried that. So the scheme will
Tried it, but did it work?
Yes. Well, yes, it did work. Yes, sorry, it did work. I should have said that, shouldn't it? It did work. So once we put the scheme, when we put the scheme in place, it will supply the district heating systems in both Campus East and Campus West.
I'm struggling to get an idea of the economics of this scheme. What is the current fuel purchase cost of the university? What's going to be the total capital cost of the project?
So I'll answer it in reverse. So the total capital cost of the project, including all the other elements of it, so the building upgrades, etc., is £40 million. The economics of it, I can't really say all the commercial things for the university because I can't remember them. But what else? The criteria for the scheme is for the public sector decarbonisation scheme. There's a criteria of £510 for total. £510 for every lifetime tonne of carbon dioxide saved, and this scheme well makes that criteria. The other thing I will mention is the cost of running, as John says, of geothermal schemes once the capital cost is in place is very, very low. It's probably the lowest way of generating heat, I would say. Yeah. Pretty much. So the cost of operation is low. Where there is
What's the current fuel bill that you're paying?
For the university? I'll answer that separately because I can't remember it off the top of my head. We've done If I can, I'll answer it in a way which might give you the information you're thinking of. The challenge that we've got as a university, and as many people is it's very cheap to produce electricity by burning gas. So from an electricity generation point of view, it's cheaper making electricity burning gas than taking electricity from the national grid. That will change. I'm sure that will change as policy changes, as we move forward.
So perhaps there's an additional, perhaps one of the points that you're maybe trying to probe is it's a very big initial outlay, that capital cost.
No, I'm very suspicious of state capital projects where they don't work out proper return on capital because they don't publish the cost properly. And I want to know what your fuel costs are for district heating at the moment and what your electricity costs are.
Yeah, I think we'll have to take that one offline in terms of the balance sheet of the university. But I think the additional point here is that this is new technology, and hence the capital cost for a pilot project like this will be higher. And the big challenge is to make it cheaper in the future. A, it's got to work, and B, it's a pilot project to see if we can do it cheaper. And hence, Paul made some reference to research, and some of that research is about what do we find when we do this, which will de-risk future projects and make them cheaper for the future. So that's part of the investment in this project. Go on, John, add to that, and then we've got a question.
Just to add a little to what both Paul and Sarah have said, we're seeing step changes in drilling rate, for example. In the US, in Utah, a government-sponsored project is drilling very, very deep indeed to produce power for data centers. And the drill rate has been increased by twice as fast, which means that the capital component of the drilling is more or less halved. As Paul also said, in this particular instance, because we don't have the failed shale gas industry essentially killed off any drilling in the UK. So we don't have the rigs. So we have to import them. So that the mobilization cost there is high. So these first-of-a-kind projects are flipping expensive, but it will change with time, both in terms of the technology for drilling and completions, and because you save by learning through the process.
There's no question we're going to learn stuff. Gentleman in the middle there.
Yes, thank you. Two linked questions, and my apologies if I missed you, the answers during your presentations. What's your target temperature that you want to reach at the bottom of the borehole, and what's your estimate of how deep you're going to have to drill to get that?
Okay, yeah, so to answer it a little bit, our main target is to look for flow, not temperature, because that's the most important success criteria. So we will, at the moment, the seismic survey will adjust the depth depending where the target is for flow. But in approximate terms, we're looking at a target of about 4.5 kilometres, and we're looking at a temperature around 120 degrees C at the exit of the, not the exit of the well, what do you call the bottom of the well?
Toe.
At the toe of the well, that's the word I was looking for.
Leg, toe. Yeah.
And how does that compare, John, to some of the other projects that you showed us?
The thermal gradient in the east of England is a little bit higher than the average in the UK. The high areas are the granites of Cornwall, the granites of the northeast beneath Weardale, and some of the Grampian granites. And they run to about 40 degrees centigrade, almost 40 degrees centigrade per kilometre, from a starting temperature of 10 at surface. So you can work it out fairly easily. The temperature profile in Brafferton near Middlesbrough, they hit 50 degrees centigrade at 1 kilometre with a well drilled in a failed petroleum exploration well drilled in the 90s. Goulby Mine, just on the north coast, you're you're 40 degrees at 1.4 kilometres there. So we're in that sort of ballpark of a mid-30s, low to mid-30s or thereabouts.
Can I indulge with a couple of questions? The first is really simple. You've obviously got a big heat source in the centre of the Earth, and the heat rises through the Earth's layers until it gets to the surface and disperses. So if you extract a vast amount of that heat in this project under York, does that mean I'm going to have to rip up all my tender plants in the garden and plant something a lot more hardy because the soil's going to drop by several degrees?
You're not the first person to ask.
The temperature of your soil is principally controlled by solar insolation, not heat from the ground. The geysers example in the US has been running long enough to understand how the systems behave over decades. They're very deep wells, very hot wells. What they've found there by putting cold water in the ground and abstracting the heat is that they chill at depth, not at surface. They chill a volume around the wellbore. And so what happens there are hundreds of wells, is that once you start to lose that temperature, you then shut it in and you let the earth replenish that heat and use another well. So wells are cycled over decade-long periods. But no, it doesn't affect the heat in underneath your plants whatsoever.
I was teasing, really.
No, but it is. We've had lots of similar questions, so it's yeah.
The second part of my question is also a bit of a tease. I wonder what a certain orange man might think about drill, baby, drill.
He loves it, bizarrely, because it fits into the drill, baby, drill. It allows the industry, which he loves even more, to permeate even further. So, strangely enough, even though it's green, and green is a very bad colour for orange people, it gets the thumbs up. And that's why the program in Utah, it's called Forge. All the data are available. There's a commercial project next door called Fervor. That's fully supported. If only we had that kind of oomph behind the UK, we'd be sailing easily.
So on the same theme then, does our own orange light support it?
Our own orange...
Mr. Farage?
Oh, haven't got a clue.
Neither has he.
But I did. I have a colleague who works with the Renewable Energy Association, and he met Trice the other day. Robert Trice, is it? Who's a Tice, sorry, apologies. Who says he thinks he supports it. Thanks. But what we're dealing with is lack of understanding. There are a handful of MPs. Rachel's very much behind it. There are a couple of other near local northeastern MPs who have picked up the baton, as it were. But getting information across is so difficult. The civil service move very, very slowly. And of course, there's a perception, oh, we'll do gas, because that's gas. We know gas, it's easy. Of course, there is a big risk, as we saw in 2022. I've been telling DESNZ and DEC before them that Russia would cause us a problem with gas sooner or later. Nobody took any notice until it happened. So because we import gas and we wouldn't be importing heat, it actually makes that energy security far more secure.
Gentleman there.
Thank you. If everything went well and you actually could heat the whole of York with it, how many wells would you need?
It's an interesting question. And I'd love to be able to answer it now, but the truth of the matter is we don't know how productive the well is. There's a few, the current well we've got, we're planning for it to give a greater capacity than what we need to make our funding obligations. You know, part of the aim is that by a significant factor. The university is quite large. You know, one well pair heats the entire university and should do quite comfortably. So it doesn't take too much thought to think what it might be able to do with 4 or 5 wells or something. One of the challenges is how do you do it, where do you do it? The drill rigs are very expensive to mobilise. They're very expensive to get in place. I'd be delighted to be in a position where we could drill more wells after we've done the testing of the first one before it leaves. You know, that's one thing I'd be really keen to, because it'd make so much economic sense, going to what my colleagues said, the gentleman over there said. But we'd have to do those numbers once we've got the assessment. Yeah. But there's a lot of power that comes out of these wells, and a lot of heat. Power as heat. Power in the streets. There comes as heat, and there is one advantage. One big advantage is if you've got heat and you take it as heat, you don't have that conversion factor of converting electricity to heat or conversion to heat. So I can't quite answer the question.
Just
but
by way of example, the one I showed in Southampton, which is a pretty rudimentary scheme, drilled originally in 1986, that well produces at 12 to 15 litres per second, and the water's at 75 degrees centigrade, so a little bit cooler than we have hoped for here, and that produces 1.7 megawatts of heat. And it has a ring main. The well site is about the size of 3 cars in a car park. It is in the car park, the old Toys R Us car park, and that ring main supplies around about 1,000 customers, I think, collectively in the centre of Southampton.
On that positive note, I think that's probably a good place, and I can't see any more hands, it's probably a good place to wrap up for the evening. So perhaps I'd like to ask Rachel to come up to say a few words.
Well, thank you so much, Sarah, for hosting this, and Paul and John for your talk this evening. It's so enlightening and so exciting. I think when I'm part of the all-party parliamentary group in Parliament, which is looking at deep geothermal, looking at the opportunities there, but making the case to government as well. And I had the good fortune just before the summer recess to meet with the Energy Minister to talk about the York project and the opportunity, but more than that, to talk about how we could see this working for our city. I think it's so exciting that this project is happening here in York, a real centre for innovation, but also ambition does not hold us back when it's looking at becoming this net zero location. And it's absolutely within the ethics and the ambition of our city that drives us forward. So to be able to produce energy which is long-term, low-cost, will address many issues. Many of you may know that this time last year I was battling the issue about so many people going cold in our country. Well, this provides a solution of addressing that huge inequality and fuel poverty, because of course once you've established your well and being able to drive that forward, you start de-risking for the current customers, users of that energy source, so that people can be guaranteed to stay well. Now, many of you will know as well that we've just passed a local plan after 77 years. We've got ambition of reviewing that. The review I've just heard today will start next year, and looking at the future local plan. Well, just imagine if we were to set 2 satellite towns around the edge of York, which is one possibility, being able to have that central heating system, district heating system across those localities. That in itself would show real self-sustainability of a whole housing development. They're the kind of possibilities that could come from this project. So it will have a massive impact on our city if we identify the source right. The big question clearly is about the establishment costs, and we need to have a look at how we can drive those down, but also to ensure that we're developing the technology here in the UK to be able to extend, because if that map isn't orange but is green, as we saw at the beginning, then our whole country can really depend on a much more sustainable source of heat. And I think that's the thing that really excites me, because we know we have to get down to net zero. It's the biggest challenge facing our government and governments across the world. And as we're approaching COP30, I hope it is this kind of discussion which is taking place, because if we get it right here, just think about where else we can use our technology, our processes across the world. And as as I mentioned, the inequality here in our own city, across the world we see it even in greater measures. So I think this could unlock not only our own energy commitments, but the global energy commitments as well, and really tackle the net zero challenge we've got. So this is exciting. It's happening here, and I really wish you every success possible, and say I'm here to back your corner as well. So I trust that we'll be able to really, in just 2.5, 3 years' time, be able to really showcase what we've been able to achieve here in York. Thank you so much.
Thank you. So thank you all very much for coming along, for your excellent questions. I suspect if you've got more, you're going to waylay these two gents on your way out. But thank you for your talks, for inspiring us, and for Rachel for her final words. And safe journey home.